The next series of videos is going into 9.2 and 19.1. Each of the videos I will let you know whether or not it is SL or HL video, whereas in the book it does not make that distinction for you. So moving into 9.2, 19.1, now we're looking at the purpose behind redox reactions and why we need to know about them and where do we use them. And one of the processes is called voltaic cells. Voltaic cells are where spontaneous redox reactions can be organized to generate an electric current. How we do this is we separate our half reactions. So if you kind of remember at the beginning of 9.1, you would have a reaction, right? And so let's just say we had copper sulfate reacts with zinc to form zinc sulfate and copper ions. Oopsies, copper. And so like this was the full reaction, and our half reactions are when we separate out each of the metals that we are reacting into what they're doing with those electrons. So what happens is we put each of these half reactions into what's called a half cell. And that half cell is a container. For us, it would be a beaker, but it could be whatever we need to build the half cell in. And you put each of the separate reactants into their separate containers. Then you would connect them through an external circuit. And that external circuit will allow electrons to flow from one cell to the next. And that creates energy, electricity, voltage. And so these guys are called electrochemical cells, also known as galvanic cells, I probably spelled that wrong, and voltaic cells. All three things mean the same thing. So just know that any of those names work. And the purpose of these are to generate an electrode potential. That electrode potential can then power energy as you see fit. And the most common example of a voltaic cell is a battery. And so we're probably going to we will be referencing batteries throughout all these videos. Now, what creates that electrode potential is the release of these electrons. Oopsie, sorry. So that movement of electrons from one half cell to the other, that is what creates the electrode potential, is that electron movement. Now, if you notice, each of these reactions are an equilibrium reaction. So when you have a solution and you have your metal in your solution, before they're connected, they're in equilibrium reactions within their own separate half cells. Once you connect them with an external circuit, they then become the full reaction that I have written below. Now, the position of that equilibrium will help us determine what the electrode potential is, and we're going to get into that differences in just a little bit. So your voltaic cells, there are two connected half cells gives you a full voltaic cell. So a voltaic cell has to have two half cells at least. And as we mentioned before, they're connected with an external wire that allows the electrons to flow from a negative to the positive half cell. So how we do that is through a process of electrodes. So you have two electrodes. One is going to be the anode and one is going to be the cathode. Anode is where oxidation occurs. So if we're looking back at the zinc and copper example on the previous slide, zinc, and you go back and look at 9.1, is more reactive than copper. So zinc is going to have the capability to become oxidized so that it is in its ion form. And it's going to release electrons. Then when it's connected to the cathode, which is where reduction occurs, because zinc is more reactive, it has a higher potential, it's going to force those copper ions to accept those electrons that zinc donated and create a copper solid, causing that movement, causing the electrode potential to be created. So voltaic cells with proper connections. All right, I'm going to draw this once, and then from there on forward, I will probably be inserting pictures because it is extensive, but you do need to know how to draw a voltaic cell. All right, so a voltaic cell is, you have your two half cells. Okay, and then in each of the half cells, you're going to have each of the reactants. So let's say in the first half cell, we are going to have a zinc sulfate solution. All right, with this, you have to have an electrode, and that electrode is typically made from the metal, the pure metal that we are reacting with. So then moving on to the other half cell, going on with our example, so this would be our aqueous solution, would be copper sulfate. And that means our other electrode would need to be the pure form of copper. All right? So then what needs to happen is we need to have an external wire in which we connect our two half cells. So this is the zinc half cell and this is the copper half cell. All right? So we have an external wire, which I'm going to make a different color. Wires are blue. No, wires are gray. So we're going to connect it to an external wire. That external wire is going to be hooked up to a voltmeter to read that voltage. And connect it to the other half cell. Okay? So then the last thing that we need to create a full half cell a full voltaic cell prior to explaining how this works is we need something called a salt bridge. So a salt bridge can either be a glass tube or absorptive paper. We use absorptive paper. It will contain or be soaked in a solution of ions, specifically either sodium nitrate or potassium nitrate, because they are strong salts and they will dissolve in solution, allowing free-floating ions to be around. All right, so here, this is the proper setup. So we have our electrical wire connected to each metal and a voltmeter, and then we have our salt bridge. The salt bridge is what actually completes the circuit. It closes the circuit so that it allows the whole process to work. So now what actually happens during a voltaic cell? All right, so once we have a complete circuit, what's going to occur is on this zinc metal, it is going to cause zinc to dissolve, the zinc metal, leaving electrons on the metal. All right, so our zinc ions are dissolving. That causes these electrons to move up and through our external wire. Our voltmeter is going to read a voltage from that electron movement. And that voltage number, which we'll discuss in a different video, is based on how willing zinc is to lose electrons and how willing copper is to accept them. So now these electrons are moving to the copper metal. That causes the copper metal to become negative. So that is allowing our copper that is in solution to precipitate onto the metal as a solid. So in a general format, in one cell where our oxidation is occurring, so our zinc cell is the anode. An anode is where oxidation occurs. This is where zinc solid is becoming a zinc ion and releasing its electrons. So this means we are starting with a reduced species, and we are creating an oxidized species. Then, as those electrons move over to the cathode is where reduction occurs. Okay, so this is where copper ions are accepting those electrons zinc gave off to cause copper to precipitate out of solution. So here, the process, you have an oxidized species becoming a reduced species. Therefore, we can look at the net reaction. So zinc solid reacts with copper ions that are in solution. Even though they're in two different half cells, they are still reacting with each other. And this allows zinc to become an ion, and we can create solid copper. So this is actually one way we can get pure copper out of a solution. But as you move through this voltmeter, so just take this as like a battery, as it moves forward, this is why batteries die. Eventually, all the zinc metal has essentially dissolved and there's no more copper ions to become a solid copper, and therefore electrons have nowhere to go, so on and so forth, and the battery dies. Now what about the salt bridge? Okay, so what the salt bridge does is it allows a neutralization to occur. So as zinc is dissolving, right, that solution is becoming more and more positive. So the anions in the salt bridge are going to move into this solution that is becoming positive to help neutralize it. And that allows the voltaic cell to run longer than it typically would. Vice versa, the copper solution is losing its positive ions due to them precipitating out. Therefore, the salt bridge is going to supply cations back into the solution to allow copper to keep being pushed out. So again, very specifically, why we have to use sodium, potassium, and nitrate is they will always stay in solution and they will not precipitate out or be oxidized or reduced during these reactions. So that is what a voltaic cell looks like. They do like to ask questions on how to draw it, explain it, parts of it. So there you go. Luckily, they have now implemented a simplified cell diagram. So hopefully this is where they're going to allow you to focus a little bit more. So the simplified version, which I like so much better, okay? So you're going to have your anode side. You're going to have your cathode side. So they're going to be separated. So on our anode, you have your more reactive metal, the metal that wants to go from a solid to its aqueous form. This solid single line I drew between them, that is called a phase boundary. So it's essentially representing the metal that we would have within our voltaic cell. Then you have a double line, and I make them a little bit longer just to help me visualize it. And then you have your cathode side. So we have our copper ions that are then going to become copper solid. And you really do write it in the form of the reaction, the net reaction, so you can represent the process in which you're moving forward. The double line here that I drew, that is your salt boundary slash voltaic, your external wire to represent that. And the last thing that you need to include, so you have your anode where oxidation occurs, you have your cathode where reduction occurs, and then you just need to draw an arrow to show which way the electrons are going to be flowing to complete the diagram. And then off to the side, depending, you would put what the voltmeter would read. So that is the simplified version, and it's a lot easier to read and draw than the complex voltaic cells. And the picture I included shows you what a setup of a voltaic cell. So you have your two solutions, and these are your zinc and copper. You can tell it's copper because it's blue. This absorptive paper, that is your salt bridge. And you can see you have your pure metals. They are hooked up to alligator clips that are then hooked up to an external wire that this reads into the voltmeter, and the voltmeter is showing you a 1.10 voltage through this reaction. So different half cells make voltaic cells with different voltages. So it all depends on what's in those half cells. And the direction of electron flow and voltage generated is going to be determined by the different reducing strengths. Therefore, you need to look at and become very familiar with the reactivity series that are used. So we did zinc and copper, and we saw that that had a plus 1.10 volts. If we look at a different series, okay, and I'm just going to use simplified diagrams. So let's look at zinc again. Zinc solid, going to the zinc ions, and then we're looking at silver. And so if you look at the reactivity series, you would see that silver is still below zinc. Therefore, zinc needs to be written first, and it is in the anode half cell. So we have our simplified version drawn, and looking at the voltage, you would get a 1.56 volts for this voltaic cell. This represents the fact that zinc has, or the differences between the zinc and silver and their placement in the reactivity series is larger, and therefore zinc is able to force even more silver out of solution, creating a larger voltage. So what's going on in each of our half cells? So we know zinc is being oxidized, therefore it's going into its ion form, releasing electrons. And that means silver is being reduced, and it is accepting those electrons to come out of solution. So our net reaction is going to be zinc is reacting with two silvers to form zinc ions and solid silver at a relatively high voltage. So then we could look at, well, if zinc had the capability to reduce copper and it has the ability to reduce silver, what if we put copper and silver together? Now, if you look at the reactivity series, you see that copper is above silver. And so we'd write copper first, and the fact that copper would be the oxidized species, so it's at the anode, causing silver to be reduced at the cathode. Right? And so when you go, and this would, because they're closer together in the reactivity series, creates a a smaller amount of voltage created, but it still is a voltage. So that is showing us in our complete reaction of copper reacting with silver, makes copper ions and solid silver, right? That shows us that copper has the greater reducing power, forcing silver to be reduced and copper to be oxidized. And so depending on what the half cells are and what they look like and what their makeups are, you're going to have to determine who's going to be oxidized, who's going to be reduced. Therefore, you know who's going to be at the anode, who's going to be at the cathode, which directions the electrons are going to go, and therefore you can create a net reaction and then determine what the voltage difference is going to be.